Hello, ladies and gentlemen. My name is Jerzy Baranowski, and welcome to our second lecture in the course of machine learning for the second level studies of automatic control and robotics. This lecture is non-standard thing because this lecture was supposed to happen uh, in person, and there will be no will not be recording that. But well, life happened. I'm currently away, and the person that was supposed to replace me got sick. So we are where we are, and I will give you this lecture, which I'm recording a day before actual lecture happening. Is during the middle of the night, so be uh, let's say considerate about that. Uh, the main point of this lecture today is to show you the Gaussian processes to prepare you for the laboratory exercises. However, this lecture of course will be minimally edited because of the time constraints, and it will not be for long on the website, so on the channel, so probably it will be removed after some time. So let us focus on actual topic of this lecture, which will be Gaussian processes for regression and classification. So we are extending the ideas from the previous lecture when we've moved to ensemble methods, and we've talked briefly about the ideas of Bayesian model averaging, which I highlighted that it is related to the issue of Gaussian processes. So in this lecture, we'll try to discuss what's the role of Gaussian process uncertainty estimation. We'll try to move to mathematical foundation and show what are kernels, how regression and classification methods work in the framework of Gaussian processes. We discuss a bit about computational challenges and sparse approximations. Then we'll move to how to do it in full Bayesian treatment via Markov chain Monte Carlo methods. We'll show a bit of forecasting case study on artificial data, and finally we'll give you a bit of highlights when to pick Gaussian processes and not standard neural or other machine learning models. So let's start with our motivation for what we are doing. Generally, in most of machine learning applications, we want to create some kind of method to represent function between data and the outcomes. And in most of those models, we construct some kind of parametric structure. We start with, in case of linear regression, this is just linear combination. In case of some kind of trees, we have a tree. In case of ensembles, we have multiples of trees or other simple models. In case of neural networks, we of course have lots and lots of neurons. And the idea is that in Gaussian processes, we do not assume actual functional form. We define a probability distribution of the functions, and we try to determine what is the average best, what is the expected function from this distribution. And this is a generally extension of mentioned before Bayesian model averaging, because we, instead of integrating over models, so trying to combine multiple models, we are integrating over the entire functions. And this works because this probability framework allows us certain applications regarding uncertainty estimations, because not always our models, our data are sufficiently good that we are absolutely sure what we are doing. And typical machine learning models do not provide us with proper uncertainty methods. So that's where the Gaussian processes lie in modern machine learning, and we'll move to show you some kind of ideas how it works. So, as we already know, I've talked about it multiple times before, including last year's lecture. Machine learning models usually give you point predictions, which, because do not have any kind of uncertainty estimation, can be overconfident. And in case of safety critical or high cost domains, the fact that what we can predict is one thing, but knowing that we can't predict something with good precision is also very important. That's why we do not disregard probabilistic model even in more complicated, more data intensive solutions, because we want to have some kind of information about the uncertainty. And Gaussian processes are very nice in this way because they are kind of solvable numerically and can offer us certain flexible non-parametric Bayesian way to model uncertainty in a way. So it's very good for such cases as forecasting or anomaly detection when we are not sure that something is an anomaly, but we want to at least give something a confidence interval, and when we are predicting something, we need to be aware how wrong can we be. So generally, Gaussian processes give us the most flexibility, the best solution regarding the uncertainty of our regression. So in case of such situation, we can kind of interpret this function representation in a way that we can know what kind of assumptions we've given regarding the smoothness of the functions or regarding the actual correlations between points. So those things can be made interpretable a bit. Well, of course, getting function from a distribution has certain understanding limitations. They can work in very well for in small to medium-sized data sets up to a few thousand points, because otherwise there will be issues, which we'll see later, because there can be some big matrices to handle. However, they can be used in multiple situations. The most relevant one is so-called Bayesian optimization, when we want to create, to minimize certain functions we don't know, and we try to use Gaussian process as a model of that function in order to find that its expected minimum. But also other important aspects are spatial models, especially kriging, in case of interpreting geographical data. Also deep kernel learnings. In those things we need interpretation of use of our Gaussian process, because they give us enough flexibility without at the same time reasonable assumption handling. And as we mentioned last week, we discussed the Bayesian model averaging combines models by integrating over model weights, and GPs kind of extend this concept, because we are not averaging discrete models. We kind of integrate over infinite family of functions in order to get an expected function in a way. And each function has its own prior probability determined by its so-called covariance kernel, which we'll cover in a moment. And our prediction will be kind of, in a sense, it will be an expected value or otherwise weighted average of all possible functions given data. To get some kind of intuition, we want to construct GPs in a way to specify what kind of functional relationships we actually want to expect to model before seeing the data. And they are defined by two things: mean function and covariance function, because Gaussian processes is a kind of, in a way, like a multivariate normal distribution, so a vector valued normal distribution, but for infinite vectors. And in practice, it reduces often to just something from finite vectors, like in any other dynamic optimization problems you can encounter. However, generally, sampling from a Gaussian process prior gives us random smooth function consistent with the kernel that defines the covariance. So we need to understand one thing. If we have a normal, multivariate normal distribution, the covariance is just a matrix. Because in case of functions we have infinitely many points in the vector, we cannot define an infinite matrix. Maybe we can, but generally we can define it by defining so-called covariance function, otherwise kernel, that just represents actual values depending on which points are in this matrix. So it's like this matrix of infinite points. We can kind of compute these these elements of this matrix for any given 2 points using the covariance function. And having this prior specification that specifies the covariance function and the mean function, we can condition it, of course, on the data and update the posterior Gaussian process distribution. And it is, of course, important that we need to remember to treat Gaussian process prior as the same as priors in any kind of models. We have certain possibilities of prior predictive distributions. We can see what kind of data can be generated from this model, etc. So just to get some kind of visual intuition, if we sample function from priors, for example, from so-called radial basis kernel function, we will get certain functions that can be wiggly in different ways. And generally, in most cases, we have 2 important parameters that are specified in the kernels. We can have it in more specialized kernels, but the most important are length scale. So generally, how related are points between each other? So how stronger correlation between far away points on in the function, and the other is variance. So how wiggly the function is, how large scale of values it can take. And having that, we can move to actual mathematical foundation and connection to the kernel methods. So we try to define the Gaussian process. We'll try to define the mean and convergence functions more precisely and connect with the kernel methods and some kind of predictive equations. So, in a sense, Gaussian process is a collection of random variables defined on the set of x. Will be the f of x for given x in certain set, in such way that every finite subset follows a multivariate normal distribution. So, speaking of that intuition of infinite vector before, so they defined in every point of the function, whenever we limit that vector to be finite in any way by taking some points away, because of the kernel function, we can construct the normal distribution that will be relating all those functions, independent of what those points are, the x points for which we can compute our Gaussian process. And of course, in that case, we will have a mean function and its covariance. In most practical cases, we don't talk much about mean function because usually we can assume it's 0 because we use Gaussian process to kind of model something that is not modelable in any other way or has more random structure. We use the notation similar to a normal distribution, but instead of writing normal distribution, we write a GP, so Gaussian process dependent on mean function and the covariance function. As I mentioned before, usually a mean function is assumed 0 as long as we center our data. In very, very specific situations, if data cannot be detrended, but we know something about those trends either way, or we want to estimate those trends in a way, then we can kind of enforce something in the mean function, but it's rare situations. Covariance function, however, is not 0. Covariance defines correlation between function values, and it has the properties of symmetry, because covariance matrix has to be symmetrical, and we use the covariance function in other ways, kernel function, to create covariance matrices. So we have to get matrices. And the second thing, as the same as covariance matrix, it has to be a positive definite form. That is, it has to be give values always greater than 0. In order to construct covariance function, we use so-called kernel functions, and there are, of course, infinite number of kernel functions. The theory of creating kernel functions is relatively complicated and relies on the so-called measure theory, which is something that you are being threatened in probability course in the first year of studies. That is extremely difficult, and measure theory can be extremely difficult and can be difficult to find reasonable practical applications. However, for practitioners, measure theory is not as that relevant because usually we use the kernels that are already specified and defined that work. And most important are RBF, so radial basis function, also known as Gaussian kernel, which is not Gaussian but it's kind of called this way. The second one is Mattern kernel, which is a more complicated function dependent on certain parameters, especially the parameters of V, which specifies the smoothness, and additionally the standard hyperparameters of length scale and sigma, and finally periodic, which of course enforces periodical structure. And that's why we use them. We use them to capture certain behaviors. If we know that our relationship is very smooth, radial basis function is the best because it provides you with infinite differentiability. In case of we don't know how smooth it is, or we know that it is non-smooth, then Mattern kernels might be interesting because Mattern kernels give you the finite number of differentiability specified by the mentioned parameter V, which is not explicitly shown in the formula, but it's periodic depends on what is the period of the function on the behavior. What is important? Each of those kernels works for any number of hyperparameters. However, determination of those hyperparameters is not necessarily trivial, and we'll move to that in a second. As you can see, those kernels give us different things. In case of radial basis kernels, we get those nice smooth functions. In case of Mattern kernels, we'll get, as you can see, a lot of wiggliness, sometimes sharp edges, and in periodic kernels we will get periodic function, which can also be very wiggly. What is the connection of kernels that we use here to actual kernel methods that you've already encountered, like SVMs, kernel regressions, and stuff like that? Well, those methods use so-called kernels matrices to express similarity in the feature space, and Gaussian processes generally use the same kernels but interprets them differently in a probabilistic way. For example, a kernel regression solution is very similar to the predictive mean of the Gaussian process with Gaussian likelihood, as the actual difference depends on the parameters and actual determined variance. What is important is that Gaussian process adds the uncertainty quantification, so give us a predictive variance that we can kind of estimate what's happened in the case. And in a sense, this is just an extension of Bayesian linear regression on feature spaces. Because if we have some kind of data sets for which we compute some kind of features, we can of course create a linear model on that, just using feature with certain weights. However, the covariance of that relationship is given, of course, by the feature vectors, some kind of covariance structure, and feature vector transpose, some covariance structure, and feature vector. And the main idea is that using multiple features, this can be decomposed into a sum of certain functions of data. So the idea is to represent that sum of functions that represent all kind of feature computations from the data with some kind of one single function that can be evaluated. Because again, it's at the end of the day, this covariance will be computed if there are multiple, if there's one feature, it's just computed like this. If there are multiple features, there's always a function of a given vector of original data. So the idea is to replace this feature representation with a kernel function, which generally we can assume works on infinitely many basis functions or functions that compute features and compute that in one single function. And this defines the inner product, like here, and in a way creates a kernel function that allows us to represent the linear model with infinite number of features extracted to a dataset with a Gaussian process. And that leads us to, and actually what is very nice in this situation, that given certain training data and some kind of test input x star, we can give some kind of predictions, because knowing kernel function, we can actually get what will be the predictive mean of our model, and we can compute also the predicted variance. So knowing certain data points as here, we can compute relatively directly these the mean function, and for each point of the interval we have specified what is the variance, what is the error bar of this computation. What you can actually see, that the uncertainty is larger wherever we have less data. As when we move away from the data, the uncertainty rises. This is very nice thing, because kind of we got a formula to compute a function in any number of point x star. The problem is that this is kind of a big matrix, because it's a matrix of dimension x, where x is the data set, plus x star, the number of points we want to compute it. So if the data set is big, this computation can be rather difficult. And of course, we cannot forget that each of those cases depends on some kind of hyperparameters computed within the specifying the actual kernel, so the length scale, so the variance, etc. Okay, and that is a general problem, because as you can see here, we have to invert that matrix. We have to invert that matrix in order to get our predictive mean, and we have to invert that matrix also to get some kind of estimate of our variance. And inverting the covariance matrix can be very costly, as it requires n cube multiplications, which again can be very time consuming, especially if we want to at the same time as estimate the parameters or the hyperparameters of the model. So while actual predictions are relatively cheap to compute, because we've already inverted that matrix, the actual computation might be difficult. And there are issues. The issues are like for high dimensional inputs, when kernels which usually depend on Euclidean distance between points, they can be problematic. We've discussed the curse of dimensionality in respect of how to compute the expected value on our Bayesian course. That as the space, as the dimensionality of data or parameter space rises, then unfortunately there's an issue with that. There's a lot of empty space, and because of that, this geometry becomes complicated. We can kind of use some kind of automated relevance determination kernels, which generally work in a way in order to focus on those most relevant features and do not work on those that are less relevant. In practicality, the idea is that they kind of skew the covariance matrix towards the diagonal matrix. And always the idea in order to work with GPs in high dimension is to kind of you reduce the parameter space, the data space, and dimensionality reduction is not a bad idea, and we'll be discussing dimensionality reduction in our next lecture, which will be hopefully happen in person. Other idea is to kind of approximate the matrix in a way that it will be easily invertible and has lots of zeros, so be a sparse matrix, but we will cover in a second. So let's move to actual regression with Gaussian processes, some kind of practice and what's, So we'll kind of try to show how it works and what's going on with determination of certain points. So the main idea is that we specify the prior, so we kind of choose the mean function and the kernel. We observe the data, then we compute the posterior. We are updating the prior and we predict our new values. So the main idea is of course that we can. This is being done for us in simple cases. So generally, we kind of specify our kernel here with given length scale, with given noise level. Then we fit the Gaussian process using the marginal likelihood optimization, which is specified in the function Gaussian process regressor in the Gaussian process regressor in the sklearn, for example. And of course, as standard with Gaussian with sklearn, we have a method fit. Give me a second. I just needed to change something, which didn't help, but whatever. Okay, so I wanted it so it wouldn't be red, but it still is. Okay, so generally predictions are computed by just using appropriate method of GP predict, and if we get the standard deviation, we can then reformulate it into construct appropriate visualization. The idea is that changing the kernel, we have multiple influences on our product. Again, if we use the RBF kernel, we'll get very smooth stationary correlations. In the case of Maton, we'll get less smooth, rougher function. In case of periodic, we can use it to model repeating pattern like seasonal data. Finally, we can combine those kernels in multiple ways. We can sum them, so our kernel would be a sum of other kernels, and for example, we can represent additive trends, like long-term trend and a seasonal trend, or we can use a product structure. So we can, for example, install some kind of local periodicity by proper multiplication of that. And the hyperparameters of our Gaussian processes, so like the length scale, the Maton parameters, the noise variance, are determined by maximizing the log marginal likelihood. So generally, some kind of specified to the case likelihood function. In usually, as we always know, we were working with some kind of sum of squares usually. It should work in a way that will balance the data fit and model complexity, because it depends on number of samples and other things. This is of course done using the sklearn method fit, which is calls proper optimization methods in order to maximize the log marginal likelihood. As you might remember from last year, from my lecture on Bayesian statistics, its maximization of likelihood has certain limitations, and the more result will be non-normal, the bigger the limitation will be. So it needs to be aware about that limitation. This is of course not true posterior computation, because as I mentioned, it requires actual MCMC computation, but this is so-called type 2 maximum likelihood estimate. And depending on how we set those parameters, we will get different regressions. If we use our model with different length scales without optimization, you can see that if a shorter length scale causes the function to be much more wiggly. The longer length scale enforces smoothness. This can, of course, cause that for smaller length scales we can get some kind of overfit, and in case of too large length scale, we can get an underfit. So both those cases might be problematic. So again, we need to find some kind of golden middle. The same happens for noise level predictions, because increasing noise levels will either increase overfit or underfit and increase the uncertainty intervals. In practice, when we are doing Gaussian process regression, we standardize our inputs and outputs. That much helps kernels to work because they have similar scales. We kind of need to evaluate our log marginal likelihood, how it will work to detect if the fit is good or not. We can use the white kernel as individual separate noise specification. That can be much more easier to estimate noise variance. As visualization of uncertainty bands is very useful, we can see where our model loses confidence. And in case of large data set, we need to focus on either downsampling or dimensionality reduction or spice approximation. And in some cases, we need to, of course, use some kind of numerical efficiency increasing tricks, like, for example, pre-computing Kolesky factors of matrix, because covariance matrices are symmetric, positive, definite, so we are not working on actual inversion but on a Kolesky factorization, which, if you remember something from numerical methods, I mentioned that they can be efficiently factorized with sparsity if certain conditions are met. Okay, so let's move to Gaussian process classification. And this is not as easy because Gaussian processes are naturally functional representation, and we cannot kind of recreate it as a classification problem. We need to do something with approximation and use some kind of modified likelihoods. Generally, of course, the idea is that if we do Gaussian process regression, we have a situation that it's a smarter linear regression. It's can be computed almost in closed form. I showed you earlier. We can get formulas for mean function and what is the mean of posterior and what is the uncertainty. That's of course not that possible. Not that's nice in case of the classification problem, because in classification, first of all, targets are not real numbers but they are discrete, and because of that, likelihood becomes a non-Gaussian, but some kind of link function has to be used, again as with regression, so they're logistic or probit. And of course we cannot solve the problems analytically. We have to use some kind of numerical computation. In the easiest way, Laplace approximation, which I mentioned some earlier, we can use the expectation propagation algorithm, which we haven't discussed, or we can use variational inference, which is actually a much more it's a very interesting and practical algorithm. What you need to remember: likelihood in case of classification problem stops being Gaussian, which makes things a bit more difficult. And the Gaussian classification model is generally based on some kind of posterior with link function, where we have the when we have some kind of usually either Bernoulli or multiclass distribution, where we can use either logit or multivariate logit or probit, and we can approximate it using the Laplace approximation, where which is kind of maximization and finding the approximating Gaussian distribution that has its covariance matrix determined using proper methods of approximation. Just to show how it generally works, it works by, as usually with sklearn, we can use Gaussian process classifier object and work on that with standard methods. What is important generally in Gaussian process classification, as I mentioned on bachelor studies in logistic regression, we do not create a classifier, we create a class membership probability estimation, because if we introduce a classifier and we just put a cutoff on 1/2, we lose a lot of information, and that can be a problem. So generally, what is important, that creating Gaussian process classifier, we get this function that represents our membership. This is of course a very simple 1D binary case, like solvable with single if, of course, but that's not the point in this case. In this case, is just you can see certain things, that Gaussian process classifier is confident when it has a lot of data regarding in certain points of space. If it has less than, well, then its probability estimate reduces. So this is good in order to get some kind of uncertainty quantification. And if you don't use probability estimations, you don't use predict proba, you get outputs 0, 1, you lose all that information, because you don't know that here the model did not have that much certainty about it. And decision boundaries in Gaussian process classifiers are smooth and probabilistic, and as I mentioned, confidence decreases far away from data. The posterior variance grows in that cases, and this is again similar to SVMs, but because it introduces this probability element, it kind of introduces the information about uncertainty in much more practical way. Generally, when we want to compute the Gaussian process classifier, we have multiple options to do so. The simplest one is Laplace approximation, which, as I mentioned, it's a Gaussian, it's fitting a Gaussian around maximum a posteriori model, which is relatively simple, relatively fast, may completely fail on uncertainty as the more degenerate the posterior is. Expectation propagation is something that we have not discussed on any of other courses, and we probably won't, because it is based on it's kind of not that fast as Laplace, not as good as MCMC. MCMC is getting better and better, and variational, we weren't discussing on Bayesian course, because variational methods are not that well cooked for typical Bayesian models. They work much better in machine learning applications. So generally, expectation propagation works on moment matching. That is, we want to create the representation that is that has this probabilistic representation that will have the same moments as the posterior that we can have, and it can be the rather complex, can diverge, but in many cases very accurate. Variational approximation is interesting because it's based on something called Kullback-Leibler divergence, which I might have mentioned last year, but very tangentially. And this Kullback-Leibler divergence is generally a metric that specifies how one probability distribution differs from one another. And in case of variational approximation, the idea is to approximate the actual posterior with some kind of probability distribution that will have small difference between posterior in the difference between posterior and that function will be small, but because we don't know the actual posterior, we kind of estimate it with the certain lower evidence bound, and we want to find a distribution representation that can be that can minimize that lower bound on the evidence. Generally, this is most scalable method of Bayesian computation. It is stable, it is relatively fast, however, it can get you some biases in posterior because you are limiting your posterior to a certain class of functions. It might not necessarily be a normal distribution, it might be something more complicated, some mixture or something else, but still you have limitations that can be very problematic, and especially if the posterior is weird, the evidence lower bound might be biased in certain ways. And finally, MCMC, which you already know from the next year, when you sample the true posterior, and it's very accurate, but the more complicated problem, the more expensive it becomes. And that leads us to our discussion of computational challenges and sparse approximations, because first of all, we have a problem with the size of the matrix that we need to analyze. The cost of n cubed multiplications can be large when n is large, and it even becomes even stronger in, for example, Bayesian MCMC computation, where you have to compute the factorization of covariance matrix in every step. There are some issues regarding covariance structure intuition. We will discuss a bit of sparse methods. We'll try to move to more variational approximations and higher dimensional inputs. So, as I mentioned before, n cube is a lot. Cholesky decomposition is the biggest bottleneck in practical Gaussian process usage, because it can become very cost prohibitive very quickly. If the matrix isn't sparse and you don't use proper methods, and spoiler, there are not that much libraries that can exploit that, because if you have, especially in case of Markov chain Monte Carlo framework, because if you have a dynamically changing Cholesky factors or generally covariance matrix, because it depends on the hyperparameters, there might be problems, especially in any kind of fast computation, which we would like in some kind of scalable solutions. If we know the structure, the problem is not existent, but then it's something else. So generally, we have this matrix that is relatively dense, or can be relatively dense, and because of that, it's hard to inverse. So the idea is to kind of exploit this covariance matrix structure in a way that will make our computation easier, and at the same time does not introduce much problems. And the problem is, of course, that not every point is correlated with each one in the same way. They are correlated in very different ways. And in that case, and usually they are most correlated with points that are next to one another. So the idea is to do some kind of quantization, to kind of either use local kernels that will just work in certain areas of the covariance matrix, or just approximate small points to zero, so do some kind of pruning on this matrix in order to efficiently work it, and then get a sparse matrix which you do not represent those points at all. You focus only on that, and you do some efficient sparse computation on that. That will be the general point. So the idea of using these sparse Gaussian processes is to kind of, instead of working on full covariance matrices, use some kind of low rank approximations of those matrices that will kind of behave properly. You can determine certain so-called inducing points that will be summarizing our function globally, and that would reduce the computation drastically, because if we use less points, that will be well more represented, and other points will be kind of their influence will be kind of reduced, then you can reduce the cost significantly from on cube to on times m squared, which m is the number of those inducing points. And generally, there are few methods that work for sparse Gaussian processes. The most well-known are FITC, so the fully independent training conditional, where each point is conditionally independent given inducing points, which is a classical one. Variational free energy is a variational bound on log marginal likelihood, and it's stably and widely used. And stochastic variational GPs is a way of mini-batch variational training for large data sets, which kind of should scale to millions of points. Both FITC and VFE are early formulation. SVGP is modern and potentially practical big data. They are implemented in libraries such as GPFlow, GPyTorch, or Pyro. However, they are not implemented in sklearn. sklearn works only for non-sparse GPs, so that would work only for small data sets. For larger scalable problems, we use more advanced libraries, and we use variational methods in order to handle the computational workload. So the idea of long-range approximation is based on generally this, that instead of capturing the actual full covariance, which captures global dependencies, we only work on local dependencies, and we do that by using approximation that is block diagonal or low rank structure. What is funny that sometimes in certain models, especially in deep learning models, when we want to add some kind of Gaussian process to handle the uncertainty, there's an idea to use Kalman filters in order to propagate uncertainty through the neural networks. The idea is to use Kalman filters with generally diagonal matrices. So it's not even block diagonal, they are just diagonal, in order to improve a bit. And as we mentioned, kernel distance measures, so in case we have multiple features and our kernels include into them just distances between points computed in Euclidean spaces, there will be problems. And for that case, we kind of introduce something called automatic relevance determination, which uses different length scale for different features, which can be combined with dimensional reduction, which we'll cover on the next lecture, and that can significantly help. Or even you can go one step further and use different kernels for each feature is using multiplications of them, and that also can work, or addition, and that also can work for your model, and you can handle the problem of certain features dominating others in the distance formulations. When we are doing large scale GPs, you should be aware that going over 5,000 points can be difficult, and maybe doing subset of data or inducing point might be a good idea. Normalization is even more relevant than in the classical case. Variational approximations generally are current standard, and all the people are using it. You need to, as you are monitoring the loss functions in any kind of deep learning models or any kind of training models, you should also convergence of marginal likelihood and evidence lower bound. Uh, Finally, mini batching is a way to go. It's being used in SVGP with a lot of success with using some kind of scalability for those models. But what if we want to use full Bayesian treatment and don't work on computation and want to use Markov chain Monte Carlo? Well, that is a situation that it is sometimes useful. And we'll do a bit return to Stan, which we covered last semester. Generally, in things we did before, we optimize hyperparameters by maximizing some kind of marginal likelihood, and then we handle the large matrices that are coming there. But that it causes the issue that hyperparameters of the kernel are point estimates. So we don't have any uncertainty about those points. We have only uncertainty about prediction. And sometimes it is relevant. So in full Bayesian treatment, we provide priors for those hyperparameters, and then we integrate them out, or in the practical case, we compute them using Markov chain Monte Carlo. So let's say we get a simple model in Stan. This is a very simple model with a set of data, a set of output variables. We have three parameters, so the length scale, signal variance, and noise, and we have our kernels using the defined through our matrix here. This is not efficient way, but we generally work on a Gaussian process as it would be a multinormal distribution on given n. And the idea is that because we provide priors for all the hyperparameters, our posterior will not only be posterior on the data, but also will be posterior on those parameters, which will give us some kind of uncertainty distribution. And that can of course be done using just command stand pi, which you already know before, just by sampling our models with 4 chains, and we can get samples of posteriors of all those hyperparameters that we wanted, and then we can do some things about it. For example, kind of compute what's going on. And that allows, of course, posterior predictive analysis, so we can, instead of creating the visualization of our probability distribution just as a mean plus standard deviations, we can just compute, as in traditional Bayesian framework, we can just compute those multiple functions at the same time with different time scales and then average them, providing more robust uncertainty bands that reflect both observation noise and hyperparameter uncertainty. Generally, full Bayesian is slow, but give us full posterior information at point estimates, give us full uncertainty information, handles much smaller data sets, and is for very specific applications. So let's do an example to show what can we do with Bayesian Gaussian processes, and we can use them, for example, from time series predictions. We will be doing a simple energy consumption data set, which we'll create artificially in order to get something that will work without an issue, and we can see effectiveness. So the main idea is that, of course, like energy demand forecasting needs both accuracy and uncertainty estimates. Point estimates, if we are predicting the energy consumption, is of course irrelevant, because if we base on that our electricity production, we will have either large surpluses and losses, or we have lags of energy in the network. Both things are problematic. So we have to be able to handle multiple situations. That is important for grid stability, that's important for maintenance scheduling, that's important for economic planning. And deterministic models such as neural networks or ARIMA have all the limitations of time series models that we've discussed last year during the analysis and databases courses, for example, and so give us very limited predictions. Gaussian processes can handle at the same time seasonality, long-term trends, and different noise with credible interface. What is important, Gaussian processes are kind of a part of Prophet from Meta. Let's get a synthetic data set. We'll just include certain linear trends. We'll include certain average value, and we'll include the daily periodicity and weekly periodicity. So, of course, some random noise in order to. So, like we can get some kind of. There is a pattern here. It's kind of complicated, but it's kind of handleable if we want to do it the right way. For time series forecasting, we need to use some kind of composite kernel, so we need something that will be able to handle both our periodicity that we can expect. So we have the periods of our kernels we have already know, and we need to something that needs to capture our long-term smooth trends. Because we use additive combination, we have kind of different paths are corresponding for different things, can be analyzed individually. Also, this is the way the meta does it. So if you want to know in Prophet, so that's how it works. Using a demo in Python, we've split our data sets into a train and test functions. So we, after 160 days, we get the we just get bare predictions, which are not influencing the data from here, are not influencing our model. And of course, we define kernel, as you can see, very easily just by combining the objects. And we use the same things as always, just standard structure of the sklearn for any kind of model. And as you can see, it works relatively well. Evaluation of such models generally is the you should use multiple metrics just in case how it works. You can use both root mean square error and the mean absolute error, and they have different interpretation because root mean square error is kind of as similar to a kind of estimation of variance in a sense, and if signal has a lot of variance by itself, it just it includes the changes in RMSE might be irrelevant by itself. In case of mean absolute error, generally absolute errors are more useful in practical situations because they penalize more practical issues than root mean square errors. Also, continuous ranked probability score should be used accounts for both mean and spread of predicted distribution, which is unfortunately not implemented in sklearn, but can be easily computed by proper scoring or by xskill score. So like there are functions for that. Generally, RMSA and MAE evaluate the point accuracy, and CRPS measures quality of probability forecasts. As we can see what we got here, we can see that our GP captures trend and periodicity accurately. Of course, this was very simple trend and very simple periodicity, but like again, doing something on practical real data during lecture to show an example how it works would require deep studies in how and what kind of effects can influence the actual real consumption. Predictive uncertainty is of course narrow in the training range. It becomes larger in the future. The intervals are farther and farther the farther away we get from data. Our hyperparameters correspond to physical cycle length, so this is interpretable in a way that we can kind of decompose what is the effects of daily and weekly loads on our system. Generally, what we need to know when we compare Gaussian processes to neural networks is that there are different methods for different purposes, as always. Uh, Gaussian process have always give you the uncertainty measure, which is very good things, which can be very difficult to done in neural networks, require you very specific methods to do so. Gaussian process will work with smaller data sets and generally will work with smaller data sets. The idea for larger data sets requires some kind of approximation which might be limited. Neural networks will need larger data sets, and that's it. Interpretability to the level of kernel components is easy. Going deeper might be more difficult. Neural network is just not interpretable. Scalability, on the other hand, is much more relevant in the neural network scale. Okay, so generally when we want to use those things, and I think I duplicated some slides. Generally, everything will work. GPs will work for smaller data sets where neural network will fail. On medium-sized data, you need to handle it specifically with GPs, which is not a problem for neural networks because they can be possibly tuned. For large data sets, the Gaussian processes are just infeasible. They are not scalable enough. And neural networks shine there, but not all problems are large data problems. And you also need to be aware of that. And there are problems that you have very, very limited data, but you need still to have to something. And in high dimensionality, well, in both cases, you have to do something. Either you need to, in case of Gaussian processes, you need to some kind of way to handle features and their correspondence with each other. In kind of neural networks, you have to use proper architecture that will handle so many features in a way. On a qualitative point of view, Gaussian processes are non-parametric and kernel-based, while neural networks are parametric, which can be good, can be bad. Gaussian processes, of course, also are in practice parametric, but in theory, in understanding of them, they are non-parametric. In Gaussian process is always trained on some kind of Bayesian inference, sometimes very simplified one. Neural networks, on the other hand, is just an optimization problem. Uncertainty is a strong point of Gaussian processes. Neural networks, not really. Interpretability is much higher. Scalability is much lower. Hyperparameters are kind of interpretable. That's an advantage of Gaussian processes. Length scales, variances, they are things that you can understand. Hyperparameters of neural network training are magic, and fitting them can be very difficult. But of course, neural networks have different applications, right? Simple regression, forecasting, or calibration are very good points for Gaussian processes. What is important in predictive uncertainty? Generally, credible intervals are wider when we don't have data, which kind of makes sense because if we don't have an anchor to our predictions are much less certain. And of course, uncertainty is naturally obtained from that. In case of neural network, if you do not introduce specific explicit modeling of uncertainty, you have generally constant variance of some kind, which can be very overconfident. Let's move to some practicalities and go at how to use it. So, I'm saying it third time today, standardize your features and outputs for Gaussian processes, especially in higher dimensions. Kernel should make sense and represent some kind of domain knowledge. So depending on, you usually know something about relationships you want to model. And the smoothness is something that kind of can be inferred from interview with people or just by process analysis. Length scales, the same thing. So selecting proper kernel is important. Uh, you need to analyze the marginal likelihood that comes from the computation and how it behaves during the optimization, and what are the values of length parameters and do they make sense, because length scale is kind of interpretable. So if it gets weird, then maybe you need to look at your dataset or your model. Visualization of posterior uncertainty is a must, because if we do not analyze the posterior uncertainty, then why we are using Gaussian processes anyway? For large data, you need to use some kind of approximation, and there are methods implemented in proper libraries that can handle sparse and variational approximations. And you can do some deep structure using deep kernels or hybrid models, but that's not for this lecture for today. Generally, in case some kind of observation on what you can do when something happens. If you have very small length scales, you get overfitting and some kind of weird oscillations. So you need to handle that, and either you need to add bounds for those parameters during optimization or modify the priors if you're using MCMC. If you don't data scale, kernel won't fit, you need to normalize. If you are doing the damage reduction, so downsampling, and use not enough inducing points, you will just underfitting, so you have to either move them to different places or increase their number. If the problem it becomes poor, there are issues with numerical stability, it happens because of divergences in Cholesky matrix, because in some configurations, while the covariance matrix should be positive definite because kernel is positive definite, the rounding errors can bite you, and perhaps adding some kind of jitter might help. Finally, if you are using Gaussian processes to extrapolate something that is very far away from data, then you might have issues with what you are actually extrapolating. So remember that the farther away you get from data, the higher the uncertainty bands become. So you need to be aware that you know less and less. Just to give some takeaways. GPs define distribution over functions, and because of that allow us to look for functions in a more complicated environments. Predictive mean is kind of kernel weighted interpolation, which has its own predictive variance, which is kind of an uncertainty estimate. Kernel, because of the hyperparameters, give us information about smoothness and periodicity and other stuff in function and length scales. So changing that introduces consequences. Scaling of the problem is difficult. So keep it to a smaller model or use the sparse and variational approximation to do that. Gaussian processes do not compete with deep learning models. They are for different things. They are for small tasks with request interpretability and have uncertainty critical tasks. Neural networks are for large-scale, high-dimensional problems which do not require interpretability or uncertainty estimates. What to read? Again, Murphy is a good point to do, which is in the introduction. Generally, everything here is free. Rasmussen is a classical text on Gaussian processes. You can find a PDF online on the website of the author. So it's free and free. Murphy is generally free by the author, but it's a big book. Together with Dr. Dudek, we have wrote 2 papers that might be some kind of interest, especially this one, which shows you application where Gaussian process can be used. So if you can, both of those papers are available online in open access format, so you can find them. Documentation of GPFlow and GPyTorch gives you the documentation for scalable GP implementations. I am sorry that it was so fast and potentially not legible, but first of all, this is late when I'm recording it. Second, I planned it to give it in person, and it happened what happened. So thank you very much to those who listened, and our next lecture will be hopefully in the in-person format. Thank you very much.